Hi guys, this is Algebra 1. Are you ready for the last lesson for topic 5? Ready or not, here it comes. 5-4, transformations of piecewise defined functions. And this is the last lesson of the topic. So we've learned about transformations. We learned piecewise defined functions in this topic. We're gonna put it together and see how piecewise defined functions transform using graph and algebra. So let's look at model and discuss question. Cleo takes 3 one-hour classes at a community college. The graph shows the time she spends in each class. Okay. Next semester, each class will start an hour later. How will this change the graph? So look at the graph. He has the first class from 8 a.m. to 9 a.m. Second class from 9 to 10 a.m. Third class from 10 to 11 a.m. Okay, so the x-axis represents the time for the class, and the y-axis represents the class, the different classes, right? So if each class starts an hour later, so class 1 starting at 8 a.m. until 8 a.m. until 9 a.m. pushes back an hour later. Class 2 pushes back an hour later, 10 to 11, and class 3, 10 to 11 becomes 11 to 12. Okay, it'll change like this. How will the graph change if she takes 2 90-minute classes? One starting at 8:30 a.m. and the second at 10 a.m. So what if she has 2 90-minute classes? So an hour and a half, right? Starting at 8:30. So class 1 could start here, but it's 90 minutes, so it's an hour and a half. So it ends at 10. But the second one starts from 10 to 11:30. So that would be 2 classes she would take. Okay. So these are some transformations we can make from the original function, the step function. Okay. So this is the red one is part B. Green one was part A. Okay. Let's do blue for C. Part C, starting in the fall, Cleo will take 3 classes in a row, with the first starting at 7 a.m. Cleo says that she can update the graph by moving all 3 steps 1 unit to the left. Do you agree? She'll take 3 classes in a row, with the first starting at 7 a.m., right? 7 a.m. So, 3 classes in a row. So we're using the same original graph, but they're gonna be in a row, so no break time. Here. Okay, so how did the graph change? Is it really moving all 3 steps on 1 unit to the left? No, if she shifts the graph left 1 unit, she's starting 3 classes at 7:30 a.m. because this is 7 a.m., right? That 1 unit represents 30 minutes here. So 2 units would be an hour. So Cleo have to shift each step 2 units to the left to show the classes starting at 7 a.m. Let's record that. No, if she moves 1 unit left, she starts at 7:30 a.m., not 7. So she needs to shift each step 2 units to the left. Okay. So that was an example of moving and shifting, transforming step function. So let's think about how we can, how the constants affect the graphs of piecewise defined functions. So how can we use constants to move and transform piecewise defined functions would be the main idea. Example 1, translate step functions. Uptown Sandwich Shop is increasing the number of bonus points by 2 in the shop's rewards program. Fun. How will the total points awarded for a $3.8 item change? So look at this graph. Look at this visual here. Uptown Sandwich Shop Rewards Program says 1 point for each $1 you spend plus 5 bonus points for each visit. No fractional points awarded, so only whole numbers. And it's going to increase the number of bonus points by 2. So 2 points for each $1 you spend plus 7 bonus points for each visit. Okay. So how much will the total points be awarded for $3.8 item change? So if you pay a visit, you get 7 bonus points. And then 3.8, so every $1, so you spend $3, right? You need to round down because they only give you 2 points. So now upgraded to 2 points. They only award you points for every $1. So you have $3 eligible, 3 whole number dollars. So 3 times 2, 6, right? So 7 plus 6 is 13 would be your total points. But look at another notation here. Int means integer. Okay, you can use the integer function on a graphing calculator, or you can put it in Desmos as well to graph the functions. Let's go to Desmos. Okay, so in graphing calculator, you can use something called int, but in Desmos, you will have to use either the floor or the ceiling. In this case, you're rounding down for every decimal you go up, right? If you spend 3.8, they only count the $3. So you're rounding down, okay? So this is gonna be a floor function. You can put into Desmos f of x equals floor, type in floor, parentheses x plus 5 is your original graph. And then after it's transformation, let's use g of x equals floor function of x plus 7. Okay, so let's change the color so that we can differentiate. Let's match the textbook so that the blue is the original one and the transformation is in red. Okay, so before is blue here, right? And then after you start with 7 points if you pay a visit. So before, if you pay a visit, it's 5 points automatic, 5 points. But you start with 7 points now because you add 2 points. Okay. So the graph is overall translated up 2 units, right? All the steps are translated up 2 units. All right. So the points for $3.8 item increase from 3.8 would be here, from $8 to $10, 10 points. Okay, that's the whole idea. Try number 1. How will the total points awarded for a $1.25 juice drink change if the bonus points are decreased by 2 points? So starting from your original, graph. So the blue one is your original graph. If you have 1.25 juice drink, so 1.5 is here, 1.25 would be about here. Okay, 1.25. You see that? There, close enough. It's gonna be 6 points, right? It's gonna be 6 points. But if the bonus points decrease by 2 points, you have to have a transformation function where you can write h of x is equal to floor x minus, not minus, 5 minus 2 is 3. So if it decreases, the graph becomes the orange one. Okay, so from 6 points, you get 4 points only, right? Sad, but that is your answer. The total points will decrease by 2 from 6 to 4. Okay. At example 2, vertical translations of the absolute value function. How does adding a constant to the output affect the graph of f of x equals absolute value x? Let's look at an absolute value function. Let's compare the graphs of h of x equals absolute value x minus 4 and g of x equals absolute value x plus 2 with the graph of f of x equals absolute value x. So h of x is the red one right here. G of x is absolute value plus 2. And f of x is our parent function. So it starts with the original absolute value of x, right? But from here, you subtract 4 in the equation, and that's a vertical translation, 4 units down. You add 2, it's 2 units up. You see that? We did a similar one in the transformation lesson. It's the same for absolute value. Isn't that great? So the graphs have the same axis of symmetry. X is equal to 1. That means when you cut a line through x is equals 0 and you fold it, they're going to be reflected. Okay, so if you just look at the vertex and see the change, there's no compression, no stretch. It's just translation. So you can just look at the vertex and say, oh, it moved down 4 units. Oh, it moved up 2 units. Okay, so adding a constant k outside of the absolute value, important, outside, changes the value of f of x or the output. So it's a vertical change. So the value of k translates the graph vertically by k units. The axis of symmetry does not change. So try number 2. For each function, identify the vertex. Vertex is the point where the slope changes. And the axis of symmetry. Okay. So where is the vertex in this absolute value function? Without using decimals, try to figure it out by plugging in your number. Okay, and part B, g of x is absolute value minus 2. So see if you can find the vertex and the axis of symmetry before you come check answers. All right, so the vertex will start when your slope changes, which is when your x is equal to 0. Okay, so plug in 0 here and then see what it is. Absolute value 0 is 0, so plus 3 is 3. So you have a point 0, 3. If you want to double check, you can check negative numbers and positive numbers to see if the slopes change. They will. Okay. But yeah, your vertex here is 0, 3. And where's your axis of symmetry? It's just a translation. It's a vertical translation, so your axis of symmetry does not change. It's going to be x is equal to 0, or the y-axis. Okay. Part B. Same thing, 0, absolute value of 0 is 0, minus 2 is minus 2, negative 2, right? So your vertex is 0, negative 2, and your axis of symmetry is still x is equal to 0, or the y-axis. Okay, example 3, horizontal translations of the absolute value function. How does adding a constant to the input affect the graph of f of x equals absolute value x? So compare the graph g of x, absolute value x minus 4 inside the absolute value with the graph of absolute value x. So what if you add a constant inside the absolute value? What happens? This is a horizontal translation. So if you look at the vertex, there's no stretch. If you look at the graph, there's no stretch, no compression. The slopes are exactly the same. But if you look at the vertex and compare them, from 0, 0, you move the vertex 4 units to the right. So subtracting 4 here is moving 4 units to the right. So for your horizontal translation, things are gonna look the opposite way because your function is written in terms of range, and your range is your vertical translation. So it's easy to see the vertical translation right away, but horizontal transformations are gonna be written in backwards. So the opposite operation would give you the transformation. Okay. So if you add a constant h inside the absolute value bars, changes the absolute value of x, which is the input, as well as the output, because if you change the input, output depends on the input, so it does change the output as well. But it's important that it's gonna change the input first, okay? And the value of h translates the graph horizontally by h units if h is greater than 0. So if it's positive, so notice x minus h would be your form. So if you subtract a positive number, goes to the right. If you subtract a negative number, goes to the left, which means if you see x minus a number without thinking negative or positive, it's going to be going to the right. X plus a number is left, okay? All right, the axis of symmetry changes because it's moving horizontally, right? So it used to be x equals 0, but if you move 4 units to the right, axis of symmetry also changes with your horizontal movement. X is equal to 4. All right, it's where your vertex is. So axis of symmetry is the vertical line where your vertex lies. Try number 3. For each function, identify the vertex and the axis of symmetry. Come back when you're ready for answers. So again, you plug in 0. Wait, for this one, in order to figure out the vertex, you do not plug in 0. You need to figure out the vertex where x is equal to 0, right? So, wait, y is equal to 0, right? So you don't want x to be 0. In this case, you're figuring out the x-intercept. So g, your range has to be 0. So what number makes this 0? Positive 3, right? 3 minus 3 is 0. So x has to be 3. Okay, so your point is 3, 0. Instead of 0, 3, it's 3, 0. That is your vertex. Your axis of symmetry is x equals 3. Okay, that is your answer. What about part B? It needs to make 0, right? So -5 plus 5 makes it 0. So your vertex is -5, 0, and your axis of symmetry is x equals -5. Okay? Whatever your x value is, put it into a line. That is your axis of symmetry. Okay? All right, example 4, understanding vertical and horizontal translation. What information do the constants h and k provide about the graph of g of x equals as a value x minus h plus k? Now, what if horizontal and vertical translation happen together? Okay, so let's compare some examples. This is g of x equals absolute value x minus 4 minus 2. And this is g of x where absolute value is absolute value of x plus 5 plus 4 and plus 1. So you can see, you can already know that's a horizontal translation 4 units to the right. -2 outside the absolute value is 2 units down, right? What about this one? 5 units, it's plus 5, so left. Okay, outside the absolute value sign, it's either up or down. Plus 1 is 1 unit up. So if you do that together, from here, vertex 0.0, 0, you go 4 to the right, 1, 2, 3, 4, and 2 down, and you meet this vertex. Isn't that great? From here, you go 5 units to the right, 5 units to the left, 1, 2, 3, 4, 5, and 1 unit up. And there's your vertex. You see that? So you can combine horizontal and vertical translation and see both of them in the graph. I'll describe it. Try number 4. Find the vertex of the graph of each function. The vertex here would be h, k, where h is inside your parentheses, the constant, and the k is the constant outside your parentheses. Make sure you have this as a subtraction, and that's an addition, okay? So here, x minus h, h is 1, k needs to be positive k plus k, but you have negative -3. So your k must be -3. Okay, so your vertex is h, k, 1, -3. Okay, that is your answer. You don't have to figure out the axis of symmetry. Not yet. But it's going to be x is equal to 1 because your axis of symmetry is always going to be vertical. What about part B? Your h is, it's plus 2 where it's supposed to be negative, subtract 2, right? So your h must be -2 and k is positive 6. So your vertex is -2, 6. Your axis of symmetry is x equals -2. All right, example 5. Is this the last one? Yeah, no, we have some more examples. Example 5, understanding vertical stretches and compressions. How does the constant affect the graph of g of x equals a after value x? So how does a affect? Now we're going to talk about stretches and compressions. So, okay, so if you multiply a number, it's either going to be stretch or compression. It depends on how big the number is. Look at g of x equals 1/2 after value x and -4 after value x. The negative is a reflection. So 4, if you just look at the number 4, 4 is greater than 1. So it's going to be a vertical stretch. 1/2 is less than 1, greater than 0. It's going to be vertical compression. And it also looks like horizontal stretch, vertical compression, horizontal stretch, the same thing. Okay, looks the same. Vertical stretch and horizontal compression, they look the same. Okay, so if we have g of x equals a constant a, absolute value x, when your absolute value a is between 0 and 1, it's going to be vertical compression when it's outside the absolute value. When the absolute value of a is greater than 1, the vertical stretch when it's outside your vertical absolute value. When it is a negative, the graph is reflected across the x-axis. Okay, so negative sign is a different transformation. You just have to look at the absolute value of a in order to figure out if it's a stretch or compression. Okay, the value of a stretches or compresses the graph vertically because all of them is outside your absolute value. Okay, try number 5. Compare the graph of each function with the graph of absolute value. What happens? Is it a vertical stretch or vertical compression? Does it have a reflection? Then say it. Okay, part A. G of x is equal to 3 absolute value x. What happens? You have a constant a is 3. And absolute value a is also 3. So it's greater than 1. It's a vertical stretch. Okay. G of x is equal to -1/3 absolute value x in part B. You have a negative. What does that mean? It's a reflection. So reflection across the x-axis. And what about 1/3? So absolute value a is 1/3, right? And a is less than 1, greater than 0, right? So is it a vertical stretch or compression? It's a vertical compression. Okay, by a factor of 1/3. Okay, example 6. Understand transformations of the absolute value function. So putting them all together, a, h, and k all together. What if it happens all at the same time? So you will have a graph that looks like this, g of x. It has a form of g of x equals a outside of absolute value sign, and x minus h in the absolute value sign, plus k outside the absolute value. Okay? If we have that, we're going to have multiple transformation at the same time. So let's try graphing -2 absolute value x plus 3 plus 4. So we have translation 3 units to the left and 4 units up. We have a reflection because there's your a is negative and 2 is greater than 1. That is a vertical stretch. Okay, now that I've identified everything. First, you're going to plot the vertex hk, -3, 4 over here. Even if you have a, the constant a, your vertex is not going to change because it's a stretch or compression. Stretch and compression don't change your vertex. So your vertex is still h, k. So that's your vertex. And then you're going to evaluate the function to find another point, g of 0. If you plug in 0, you can substitute some numbers in your x to figure out your points. 0 plus 3 is 3 times -2 is -6 plus 4 is -2. So that's another point. And then you can sketch, this is the axis of symmetry. And it's 3 distance away, so you can go another 3 distance away horizontally, and that's going to be the reflection of the point across the axis of symmetry. Okay, so that's a simple way to graph transformation of absolute value function. Okay. All right. How can you use the constants a, h, k to write a function given its graph? So if you just have a graph, can you write a function? Yes, you can. First, you need to figure out the vertex. That is 4, 1, right? So that means that's an h and k. But how do we figure out a? Well, first of all, plug in h and k and see what you have. You just need to figure out a, right? But you can figure out the value of a by selecting another point. So the textbook chose 5. So if you have 5, you should have 5, 4 in this graph, which means if your x is 5, your y has to be 4, right? So you can plug that in. You already know h and k. So plug in 5, substitute 5 and 4 in the x and the f of x area and solve for a, which is supposed to be 3. And you can double check with another point, but your a should be the same. So now that you figured out a, you can complete your function using the form. Okay, so make sure you know the form. F of x is equal to a, absolute value x minus h plus k. Use this form to figure out a, h, and k from the graph. And that's going to be your equation. Okay, good. We're almost done. Try number 6. 6a, write a function for the graph shown using the graph. And then your part B, you're going to write the function of the graph after a translation 1 unit right and 4 units up. So after you write an equation here, write a function after the transformation here. Okay. Come back when you're ready for answers. All right, part A, that is -1, right? Your vertex is -1, 2. So it means your h is -1, k is 2. So using your function, absolute value function form, you need to have f of x is a times x minus -1, which is +1, and +2, okay? So let's simplify to a times x plus 1 plus 2. And then we need to figure out a. We're not done. Okay, so pick a good point. What's a good point? Maybe this one. Okay, this one seems nice. So that's going to be -3, 5. So put -3 in your x, 5 in your y, so that you can figure out a where it makes it true. Okay. And so 5 is equal to a times absolute value, -2 plus 2. 5 must be 2 times a because absolute value 2 is +2 plus 2. Subtract 2 on both sides. 3 is 2a. So a must be 3 over 2 or 1.5. So what is your function? F of x needs to be 1.5 absolute value x plus 1 plus 2. Okay, or you can say 3 over 2 for 1.5. All right, part B. If you translate this function 1 unit right, then you need to subtract 1 inside your absolute value sign. So in your h. 4 unit up, you're going to add 4 for your k. Okay, so your transformation will have an equation of 1.5 times absolute value. -1 is just 0, so it's just absolute value x Plus 2 plus 4 is plus 6. Okay, there you go. So these are our answers for A and B. Okay, great job, guys, hanging in there. So in summary, transformation of the absolute value function must have the form g of x equals a outside of absolute value sign, absolute value x minus h plus k, where h is changing the graph horizontally, k changes the graph vertically, and a makes a stretch or compression to the graph. And if it's a negative number, then it gives a reflection across the x-axis. Okay, and always the vertex of the graph must be h comma k. Always, always. All right, guys, that was the end of lesson 4 and the end of topic 5. So great job. It was transformations of piecewise defined functions. The topic was all about piecewise defined functions. So we learned step functions and absolute value function, greatest integer function, ceiling function, floor function, and the transformation of absolute value function. So great work. You made it here. We'll continue with the next topic in the next video. Bye.